super happy. Yeah, today we're super happy to have Dr. Jorge Mendez as our speaker. Dr. Jorge Mendez is a postdoctoral fellow at MIT CISO. He received his PhD from the GRASP lab at the UPenn. His research focuses on creating versatile, intelligent, embodied agents that accumulate knowledge over their lifetimes, leveraging techniques from transfer and multitask learning, modularity, compositionality, reinforcement learning, and task and motion planning. So his work has been recognized with an MIT IBM Distinguished Postdoctoral Fellowship, a third place of the 2 Sigma PhD Diversity Fellowship, and the Best Paper Award in the Lifelong Machine Learning Workshop at ICML. So without further ado, let's welcome Dr. Mendez.
So when every household has a home assistant robot, it is clear that these robots will have to be versatile and adaptive. We will expect these robots to have many capabilities, and each of us will expect our own robot to adapt to the particulars of our home, the chores we need from them, how we like them done, the tools and appliances at its disposal. And what's more, our preferences and needs and environment are likely to change over time. It is clear that the robot company won't be able to anticipate all scenarios each and every one of our robots will ever face in our households. So the robots will need the ability to adapt over time by learning from data. So for example, you can imagine the robot is going to use reinforcement learning to learn to tidy up our office. So it might use some amount of data to learn to move the chair out of the way, a bit more data to learn to get close to the table, grasp the folders. And so after using a whole bunch of data to learn each of the parts of the task, we get our office sorted out. And this seems pretty good. If the agent later wanted to use reinforcement learning again to learn to sort these books, the naive solution would be for it to start all over again. So it would use some data to relearn to move the chair and get close to the table, some more data to learn some new things like grasping these heavy books. And so after a whole bunch of new data, the robot learns to sort our books. And this no longer seems that good. If we wanted to have a general home assistant robot, it would require lots of data to learn each task one after the next. And the problem is that the robot is not reusing any data from those earlier household chores to reduce the amount of new things it needs to learn to solve later tasks. And this is the vanilla single task machine learning setting. Knowledge from one task is used for that task and that task only, and never transferred in any way to any subsequent task. If instead the robot was able to leverage its knowledge about navigating to objects and picking and placing stuff, we could go from this picture to this, where the robot progressively becomes more efficient at handling new tasks by building upon its accumulated knowledge. So what we need are robots that are lifelong learners, that accumulate knowledge over time to become progressively more efficient at handling new problems. These types of methods would enable robots to become substantially more versatile. The key insight that I will share today, and if you'll take away one single message from my talk, it should be this one slide, is that modularity is the key that is going to enable these capabilities. Because robot problems are modular, and modularity makes lifelong learning fundamentally easier. Let's start by looking at some of the advantages that modularity brings to lifelong learning. The robot is going to face the problem of learning tasks in sequence, one after the next. It's going to use any data it collects from each task to accumulate knowledge. And the metric that we will use to measure how well it accumulates knowledge is the efficiency of the robot at learning to solve each new task. One key requirement that algorithms will need to meet in order to achieve this accumulation of knowledge is to avoid forgetting the knowledge that they have updated in the past. So for example, intuitively, the robot might choose to very rapidly adapt to the new task and overfit to it, but that would lead it to forget the knowledge that it had accumulated in the past. And that will prevent it from reusing that knowledge in the future. So for example, if this robot accumulated some knowledge about opening doors and moving around groceries, and it decides that it will scratch that in order to specialize very quickly to opening these boxes, the robot will have to relearn all of that information about doors and groceries if it later has to face another task that requires that. The typical solution used in most of the literature today is to use one giant neural net to contain all knowledge about all the tasks. So for example, if we train this robot in the kitchen task, it might contain some knowledge about opening doors, picking boxes, milk cartons, bottles, all mixed up in this giant network of weights. If the robot then wanted to learn about opening these boxes, and it knows that it should avoid forgetting, so it wants to make sure that it retains this knowledge about doors in case it's useful in the future. The problem is that it doesn't have any way to know where in the massive tangle of weights the knowledge about doors is stored. And so it is doomed to update all the weights and potentially override some useful knowledge. Modular systems give us 3 key advantages for solving this problem. The first one is that knowledge about different parts of the task is encoded in completely isolated modules. So information from one task has no detrimental effect on modules that are not relevant to that task. The second is that the agent can progressively increase its repository of modules over time to handle a broader set of tasks. And the third is that the robot can combine its existing modules in new ways to solve more tasks compositionally. Let's now have a look at some of the ways modularity arises in robot problems. And we're going to focus on 2 forms of modularity. At the temporal level, the agent can decompose its solutions to problems into high-level abstract actions, say navigate to an object, pick it up, place it. And at a functional level, the robot can decompose the solutions to the same problems into stages of a processing pipeline. Perceive the scene, plan for how to solve the task, control the robot itself. So let's have a look at what these 2 with an example. We might have this orange arm here in charge of picking up the box and placing it in the target location to its right. So it might use some temporal modules like picking up the block, lifting it off the table, and then placing it down on the right. If we then wanted to solve a similar task with the robot arm, like placing on the shelf, it can leverage the picking and the lifting module, use a separate module for placing on the side, and immediately solve the task. But if instead we wanted to solve the same task with this black arm here, there is nothing about these temporal modules that would allow the robot to solve the task because they have become specialized to the orange arm. If instead we had a functional module for controlling the orange arm, and we replaced it by a functional module for controlling the black arm, we could leverage the detection of the block, the planning for the task, and immediately solve the task. So we have seen that robot systems and the solutions to robot problems are modular, that modularity gives us a lot of advantages for training lifelong agents, and that lifelong learning is the key toward developing versatile robots. Throughout the rest of this talk, we're going to go over 2 solutions that build off of these ideas. The first one uses neural nets to represent each of the modules, and the solution to a task is a modular net that stacks these modules one after the next. And the agent is going to be in charge of learning the interfaces between modules, so the output of each of these modules in some abstract vector space. The second solution is going to use neural nets to learn the elements of a task and motion planning system, where the TAMP system itself is going to dictate how one module communicates with the other. Compared to this TAMP-based solution, the neural net solution makes fewer assumptions about what each module should compute exactly, but requires lots of training data to figure that out, to learn those interfaces between modules. The TAMP system leverages additional engineering effort to reduce the amount of data required to learn. We're going to start off by looking at the neural net case where we're going to establish some of the advantages of modularity and compositionality. And then we're going to come back to the neurosymbolic case with TAMP. So in this first part of the talk, our goal will be to develop modular neural nets that can solve multiple robot tasks. If we succeed, we should see that the agent learns faster because each module is trained on data from multiple tasks, and that it can solve new tasks that it didn't train on by combining its modules in new ways. The tasks that this system should be able to solve are things like this. We have the orange arm in charge of placing the block on the shelf and then throwing the same block in the trash. Then we can have the same two tasks, but solved with a different object like a plate. And then we're going to have a different arm that is in charge of solving all the same four tasks. And the way we're going to do this is we're going to use one neural net to learn the grass pose for the block and one for the plate, another neural net to learn to plan the trajectory for throwing in the trash and one for the shelf, and then another neural net for learning to control the motors of the orange arm and one for the black arm. And then we're going to stack all these together into one longer net where the output of the grass pose detection module is going to give us a waypoint for the trajectory planner. The trajectory planner is going to give us a path in repurpose space for the joint space controller, and the joint space controller is going to drive the motors of the robot. So more generally, we are going to assume that problems can be represented in terms of a compositional problem graph. The idea is that the robot can solve a problem by applying a chain of functional transformations all the way from the input observation to the output action. So this doesn't really say much. This is true for any neural net policy, where each of the layers is one functional module. So the second assumption is that the agent will be able to combine the modules in multiple ways to solve more tasks. So if we can solve task A with these two modules and task B with these other two modules, this assumption says that we can solve task C and D by combining these modules in new ways. The compositional problem graph is a directed graph with two types of nodes. The first type are random variables representing the inputs and outputs of the task. So we have an input node with in degree 0 that represents the state space of a task, and an output node with out degree 0 that represents the output space of the task. And the second type of node is going to be the functional transformations, such that for an edge from F1 to F2, F2 is going to take as input the output of F1. The solution to a task is going to be a path through the graph from input to output. And the key notion here is that any function that lies on two paths in the graph is going to be part of the solution to the two problems corresponding to those paths. And then once we have this graph in place, we can use neural nets to learn each of the functional nodes in the graph. And the solution is going to be all the neural nets in a path stacked together one after the next, which is equivalent to the functional composition. So in our example, we have modules for detecting the grass pose of the block and planning the trajectory for the trash can and so on. And because of this sharing of modules across tasks, we can use these 6 modules to solve 8 tasks. And this is just a toy example. The number of tasks we can solve grows multiplicatively in the width of this graph and exponentially in the depth. So we have these neural nets. The question now is, how do we train them? We're interested in a system that faces tasks sequentially, one after the next. But we're actually going to start by looking at a simpler problem where the agent trains on a bunch of tasks all at the same time. Because if we can't solve this easier version of the problem, we stand no chance of solving the harder sequential version. And in this setting, we're going to give the agent full access to the actual graph. So it knows what task it is currently solving, and it knows what path in the graph it needs to use to solve the task. But it's going to be in charge of learning the functional modules, so the interfaces that communicate between one module and the next. And we're going to train the whole system end-to-end via reinforcement learning. So we're not going to give any intermediate supervision about what each module should compute. So the first question is, do we really care about the agent learning the right thing? the functions that we set out for them, for the modules in the compositional graph? And the answer is that we definitely care, because that is required for compositional generalization. Imagine if we trained the orange arm to place the block on the shelf, and it somehow ends up with a different functional decomposition. Maybe the grass post module learns something specific about the orange arm, and the shelf trajectory learns something specific about grasping the block. That would prevent us from solving the task with the plate, because now the trajectory for the shelf is entangled with the block grasping. And so the second question is, how do we expect to learn the right thing if we're just maximizing rewards? And the key to that is to use lots of data, or more precisely, to train the system on lots of different combinations of the modules. So we're going to train the agent to throw the block in the trash with both the orange and the black arm, and to plan the trajectory for grasping the block with both for both throwing in the trash and placing in the shelf. And that is going to prevent these systems from specializing too much. So for example, the placing the block on the shelf can't specialize to the orange arm because it wouldn't be able to maximize rewards for the black arm if it did that. So we're forcing the system to learn the right thing by having it train on many different combinations of modules. One major roadblock for evaluating these ideas is that there is no good reinforcement learning playground for robots that has these very explicit compositional relations between tasks. So I want to talk to you briefly about this benchmark that I developed with my collaborators. The key idea is to leverage our compositional problem graph to construct a large set of robot tasks. We saw that the number of tasks that we can build grows with the width and depth of this graph, where we can think of the depth as being the number of aspects that change from one task to the next. So the robot arms, the objects, the task objectives, and the width as being the number of variations of each of these aspects. So how many robot arms, how many objects. So like we've been doing, we're going to vary the object, the robot arm, the task objective. We're going to add obstacles as one additional aspect that varies between tasks. And we're going to have 4 different variations of each of these aspects. So we come up with 4 to the power of 4 reinforcement learning tasks. And by the way, this is all built on top of RoboSuites out of, I think it's folks at Stanford. So what we get looks something like this. We have this orange arm that learns to pick up the block and throw it in the trash. And then we can have the black arm do the same task, throwing the block in the trash. Then we can change the task itself and have both robots place the block on the shelf instead of throwing it in the trash. We can change the object and have both systems do the 4 tasks with the plate that requires grasping from the side instead of from the top. And then we can add obstacles to the environment that limit the free space for the robot. What's really powerful about this idea is that we can easily vary a handful of things about the environment, and we come up with hundreds of reinforcement learning tasks, each of which requires a meaningfully different behavior, but in a way that we understand exactly what changes from one task to the next. There are 2 open source versions of this benchmark, one for online training by interacting directly with the simulator, and one for offline training for learning from a fixed set of failed and successful trajectories. So do the modular neural nets we built work for these robot problems? Well, yes, these videos are of the modular net solving each of these tasks. But let's look in a little bit more detail about how well they work. We're going to train the agent on a subset of the tasks, and we're going to see how quickly it learns to solve them. And then we're also going to evaluate the system on some other tasks that it didn't train on. So for example, if the agent never learned to pick and place the block with the orange arm, but it learned to pick and place other objects with the orange arm, and it learned to pick and place the block with other arms, then we're going to see how well it can combine those modules to solve the unseen task. If we train a separate agent, a separate network to solve each task separately, we get only about 50% of the tasks solved. If we train a bigger network to try to solve all the tasks simultaneously, we don't really do much better than that. But if we use our modular algorithm we solve over 90% of the tasks within the same amount of data. And then we can compose those modules in new ways to solve the other tasks about 80% of the time. But the answer to this question is actually a little bit more nuanced than that. These results require training the robot on almost all the tasks in the benchmark. If we train on a smaller subset of the tasks, we don't get either faster training nor compositional generalization. And this is a direct consequence of the fact that we're having the system learn the interfaces between modules on its own. And that just requires lots of different training tasks. So these results are in the easier setting, where the agent gets to see a bunch of tasks all at the same time. And one implication of that is that it gets to see how updates from one task affect another. But we're interested in the lifelong setting. So let's try to study that setting now. The robot is going to face tasks one after the next, and we're going to allow it to store all the data that it wants from each task. But we're not going to allow the robot to go back in time and interact with the environment from some task that it already solved in the past. And we're also going to give the agent knowledge about exactly which task it is currently solving. Modular architectures give us several advantages for training in this lifelong setting. We get to update individual modules targeted. We get to increase the number of modules over time to handle more and more tasks. And we get to compose modules in new ways to handle more tasks. But as we just saw, this comes at the cost of requiring many different tasks during training to solve the problems. And the challenge is that in the lifelong setting, the robot initially doesn't have many tasks. It just has one, and then two, and three. One way to get around this challenge is to separate the learning process into two stages. The agent will first assimilate the current task. It'll try to use its compositional system to try to solve it, and then depart from that system to avoid making the assumption that the modules it has trained so far should work for the current task. And then it's going to accommodate any data that it obtained from the current task into the set of learned modules to improve its compositional system. So in the second stage, the agent is going to try to build the best possible compositional system for future tasks. And in the first stage, the agent is going to try to, it's going to leverage this compositional system, but it's going to explore beyond it to improve. So how can we do this? One way we can do it is we'll train a separate network for each new task we train. And we're going to initialize it from the modules that we have trained so far. So we start on the first task, and we just train normally via RL. When we jump to the second task, we're going to copy over any parameters for modules that we have already trained, and then do reinforcement learning on top of that. So the agent is going to repeat this process, training, copying over parameters for initialization, and training a reinforcement learning policy on top of that. Early in the process, the agent will have trained only a handful of these modules. And so maybe we get a little bit of an advantage over training completely from scratch, because these modules may have learned some useful internal representations. But the overall policy that we're going to construct is going to be basically random, because it has a bunch of untrained parameters. But later down the sequence, the agent will likely have trained all its modules. And so it'll be able to compose those trained modules into a fully working policy. And even if the policy doesn't work very well, the agent will still do reinforcement learning on top of that to make sure that it can solve the task. So this is the first stage. Then in the second stage, the agent will take the modules that it trained in the current task and try to combine the knowledge in those modules with any knowledge that it has accumulated so far. And the challenge is that the robot has to do it without going back to see those earlier tasks, but while maintaining the knowledge that it has accumulated throughout the sequence. So one way to enforce that the agent maintains this knowledge over time is to enforce a stricter requirement that it can still solve all the earlier tasks. With this view, we're asking the agent to maximize performance over a set of tasks without collecting any additional data for those tasks. And the key insight that allows us to solve this problem is that we can cast it as a multitask offline reinforcement learning problem. The agent will treat the data that it collected while training on each task as a fixed data set. And then it's going to optimize a model, in this case, our modular model, to solve all the actual tasks. And once we see that, we can use any off-the-shelf offline RL method applied to the modules that are used by the current task and over the data of the tasks that share some modules with the current task. So to put everything together, every time the agent faces one new task, it's going to train a separate network, copying over the parameters from the previous tasks over to the new one, and doing reinforcement learning on top of that, collecting data that it'll use for the next stage. And in the second stage, it'll use offline RL over the modules that are used by the current task and across the data of tasks that also use those modules. And then the agent is going to repeat this process throughout its lifetime. For practical reasons, we're actually going to evaluate these ideas on a simpler set of grid world domains, because training one agent sequentially on our robot benchmark would take somewhere around 3 months. So we're going to follow our compositional problem graph and construct 64 grid world tasks. And evidently, this is a simplification of our robot setting, primarily by making the state and action spaces discrete. But we maintain the key property that the agent still has to discover the interfaces between modules autonomously. We'll first look at the average reward across all the tasks, as if we had trained them all simultaneously in order to get a picture of overall performance. And what we see is that the modular agent learns substantially better than the agent that trains each task separately, individually. And we also see that we get zero-shot generalization. So before we even train on the task, by combining the modules that we have learned, we can solve the task partially. And then via reinforcement learning, we very rapidly increase performance. And then we can look at the sequential nature of the problem. So as the agent trains on more tasks, we see the zero-shot performance, and we see that the agent is progressively getting better at generalizing compositionally. It's accumulating knowledge that makes the modules work better and better over time, just like we would hope for a lifelong learner. So before moving to the next part of the talk, I'm happy to take a quick pause here to see if there are any questions. Yes, that's correct. So we have discrete variations in those parameters, and then we choose one module for each of those choices of parameters. Yeah. So we have a separate replay buffer for every task. So yeah, it continues to grow. Oh, yeah. OK, so the first question was whether we are varying parameters between one task and the next and choosing one module for each choice of parameter, to which the answer is yes. And then the second question is if the replay buffer continues to grow over time, and the answer is also yes. We only use actually 10% of that replay buffer, so we don't use the whole thing, but yeah, it continues to grow over time. Good question. Yes. So that all is learned by maximizing rewards, right? Because we're training the system on so many different combinations of things, it has to learn some abstract vector representation that can handle all the constraints of the environment that it sees. So we're not enforcing those constraints. They are learned by maximizing rewards. Does that answer your question? And then I'm going to repeat the question because I forgot again. So the question was whether we're enforcing some of the constraints, like avoiding obstacles and so on, in the modules, or if that's learned by the composition of the modules. Yeah. Yeah. So yeah, the answer is this is learned over time. So this is learned interactively by the agent. It's not enforced in the modules. Yeah. So the question now is, what do I mean by learning the interface? So the interface is the output of one module should be compatible with the input of the next module. And so that's what I mean by the interface. It's the output of each module. Good question. Yeah, one last question here.
So when you talk about assimilation and initializing these modules, how do you verify that you're not creating a module which hasn't changed? So I can see the module space exploding quickly if you continuously initialize these modules. But a large part of them could just be carried forward without.
Great question. So the question is, do we really continue to learn new modules every time we face a new task? And how do we choose, like how to avoid recreating the same module over and over again? Yeah, so the answer is in this two-stage process, we create the new network for the current task. And then once we merge it back with the rest of the knowledge, we destroy that one, right? And so we're keeping one single set of modules. But every time we learn a new task, we create a new version of that, train it on that task, and then delete it after we push it back into the rest of the modules.
I guess how do you know which are the modules? Just training where how do you know which module?
Yeah, so the question is, how do we know which modules we are destroying? So we have access to the full graph. We know which modules are reused by which tasks. Okay, so let's move on, and when we can take the rest of the questions at the end or offline. Okay, so we have seen that modularity, and specifically functional modularity, gives us a number of advantages for training lifelong robot learners. And we saw that it comes at the cost of requiring many different training tasks in order to learn those interfaces that we just talked about. There's one additional challenge with this formulation, which is that reinforcement learning methods today are great at learning short horizon policies, but they struggle when faced with longer horizon tasks, like the household chores we started out with. The key to enabling these longer horizon behaviors is to go beyond the functional modularity and incorporate temporal modularity as well. And one type of systems that embodies these two forms of modularity is task and motion planning. So TAMP systems solve robot problems by breaking them down into two levels of search. At the high level, the task planner searches over the space of abstract high-level actions like navigate to object, pick object. And then at the low level, the motion planner determines how to execute each of those high-level actions with the actual robot. So for folks with the reinforcement learning background, this is conceptually similar to hierarchical RL with options, where the task planner is analogous to the inter-option policy, and the motion planner is akin to the intra-option policy. But compared to hierarchical RL, TAMP introduces additional forms of structure, which will make it a very promising candidate for lifelong robot learning. Being a little bit more concrete, one way to solve a TAMP problem is to use classical AI planning at the task level. So we're going to use predicates to represent the state and operators to represent the high-level actions. And so in this kitchen example, we might have predicates like which object is on top of which, and whether the fridge door is open, and so on. And we're going to have operators like navigate from A to B with preconditions that tell us where this action can be executed, and effects that determine the transition from one abstract state to the next. And then we might have another action like pick up the object, and so on. And then at the low level, each of these operators is going to be tied to a low-level motion planner with some parameters. So for example, for this action, move from the counter to the fridge, the planner might get the target XY coordinates as parameters and compute a collision-free path. The overall system is built on top of a number of functional modules. The perception module computes a predicate level state from the input. The heuristic function takes these predicates and computes a ranking over actions for which might be most useful. And the task planner devises a sequence of abstract actions to solve a task. At the low level, the motion planner takes some parameters as input and devises a trajectory. The transition function determines what the final state of that trajectory would be. And our verification system checks whether that final state satisfies the constraint of the plan, of the task. And at the interface, a parameter generator produces parameters for the motion planner given the task plan. And this is the key piece that makes it possible to integrate task and motion planning. And we're going to talk about it in a lot more depth later. The system is then wrapped in a backtracking loop, which tries many different samples and many different abstract plans until it comes up with one that works, and then it executes it on the actual robot. And the plan to solve a task is a sequence or composition of high-level actions. Navigate to the fridge, open the fridge, navigate to the oatmeal, pick the oatmeal. Making decisions in this modular way is precisely what makes TAM able to solve truly long horizon problems. So each of these high-level actions is one temporal module, and we're going to represent it as a classical planning operator, augmented with a parameterized controller for executing the navigation and the picking, and a parameter sampler to generate the parameters for that controller, say the X, Y coordinates for the motion planner. The key compositional capability that we gain from TAMP is that once we have the navigation and the picking and the placing actions, we can solve multiple different tasks by combining these actions in different ways. And because TAMP systems are both temporally and functionally modular, we're going to be able to construct learning problems that are even smaller pieces of the problem. So for example, compared to the RL solution, we don't need a motion plan for the entirety of a task. We can compute motion plans separately for each part of the task. And conversely, we can separate each abstract action into multiple learning tasks. Say, learn the controller, learn the sampler, learn the dynamics function. So we end up with a collection of modules, each of which is a mostly isolated machine learning problem. And we have seen that that makes lifelong training fundamentally easier. These gains evidently do come at a cost. The reinforcement learning method that we talked about before was a fairly general machine learning solution. We could apply it to other domains like dialogue systems, autonomous driving, medical treatment planning, essentially domains where we might represent stages in a processing pipeline with neural nets and where we might want to compose the neural nets in different ways to solve different problems. By committing to TAMP as a base system, we sacrifice that generality in favor of solving robot problems that users might actually care about. As a starting point, let's focus on the problem of learning parameter samplers, because that's the key piece that makes it possible to do this form of two-level search. And it also has some interesting properties as a machine learning problem that we'll talk about. Sampling-based planning hinges on the idea that when the robot selects the high-level action to execute, it doesn't know exactly how to execute that action, but it has a motion controller with some parameters, a sampler that can generate parameters for the controller, and a verification system that checks whether the controller succeeds. For example, if we have this robot here and we wanted to push the box into the screen, it has to execute three actions: navigate to the box, grasp the box, and push. Let's focus on the navigation for a moment. The parameters for that are the delta x, delta y with respect to the center of the box. The sampling-based planner is going to try multiple versions of these x, y parameters until it comes up with a pair that comes within reach of the box and that avoids collision. But what makes this problem really hard is that the rejection sampling has to be executed in tandem with the backtracking search, because later in the plan, the robot might realize that it can't push the box in from the position it chose. So it has to backtrack until it finds a solution that enables it to push the box in. The efficiency of this form of planner depends heavily on the quality of the proposal distribution, the sampler. If the distribution is too broad, the planner is going to have to reject many samples throughout the process. If it's too narrow, it wouldn't generalize to situations where maybe there are unexpected obstacles. So the goal of sampler learning is to learn a distribution that covers the entire space of, in this case, XY positions that allow us to push the box into the screen. So let's consider the following setting. We start out with a working temp system with a sampler that works but is pretty low quality, like a uniform distribution. The agent is going to face tasks one after the next, and every time it faces a new task, it's going to use its current samplers to solve the task, and then it's going to retrain its samplers with any good parameters that it tried. The key notion here is that the rejection sampler allows us to obtain a data set of good samples given a poor sampler. And then the agent is going to repeat this process throughout the sequence of time, of tasks, learning new samplers after trying to solve the task with its previous samplers. There are three key properties of this learning problem that I want to highlight. First, the agent is faced with a natural train test loop. It is evaluated first on a problem that it had never seen before, and then it uses the data it collects from that problem to update its model to be used in future problems that it has also never seen before. The second is that the agent is going to be in charge of learning probability distributions and not classifiers or regressors. And these distributions are going to be used in conjunction with the rejection sampling. And third, the agent is in charge of learning a set of these distributions. And in particular, these distributions might be, some of them might be very similar and some of them might be quite diverse. So if we look at the specific example of navigation, it's very similar to navigate toward a chair or toward a coffee table, but navigating toward a door is fundamentally different. So how do we deal with this last problem from a modeling perspective? Do we learn a separate sampler for each type of object, one for the chair, one for the coffee table, and so on? Or do we train one single distribution across all the object types? If we have lots of data for every type of object, we almost trivially want to learn a specialized distribution for each of them. But in the lifelong setting, the agent will face new objects continually. So it won't have lots of data for new objects, and it might benefit from using data of similar objects to train its distribution. The key is that we don't need our distribution to generate only good samples. We don't need an exact model of the data. Because we have the rejection sampling, all we need is to generate mostly good samples and to generate as many good samples as possible. So what we can do is have the planner sometimes draw samples from the generic distribution, sometimes draw samples from the specialized distribution, and let the TAM system figure out which are good. So we're going to train one distribution over all the data across all types, one distribution specialized to the particular object type we're interested in. And so each of these are going to be in our work diffusion models, but we can use any type of generative model that we want. And then we're going to draw samples from the mixture distribution. And so the missing piece is, how do we determine the weights of the mixture distribution? And the key, once again, is that we want our system to generate as many good samples as possible. So we want to assign higher weight to the distribution that generates better samples. But this is a chicken and egg problem. We need to know the quality of the samples to give us the weights of the mixture, and we need the mixture components to generate samples for the TAMP system to tell us which are better. The solution is to bypass the TAMP system altogether and use some proxy to measure how good the samples are. And one useful proxy is auxiliary tasks. So the high-level idea is that we want to train our distribution and simultaneously train a supervised auxiliary model that is trained on the same data and that uses the same internal representation. The key for these auxiliary tasks to be useful is that the labels for those tasks should be quantities that are related to the samples that we want our system to generate. And those should be quantities that we can compute efficiently without going through the TAMP system. So what we'll do is every time we get a new state, we're going to compute the ground truth auxiliary label. We're going to predict the auxiliary label with our learned model. And we're going to measure how close these two are. And we're going to use that as the mixture weight. Intuitively, if the agent can generate or can predict a good, can predict well the auxiliary label in this state, it means that it has trained in sufficiently similar states that it can generalize well. And so we would expect the distribution to also generalize well in this new state. So we want to assign higher probability to that distribution. So without going into the precise detail of things, geometric signals are one family of signals that meet these criteria, because understanding the geometric consequences of a sample is essential toward understanding whether that is a promising candidate sample. So to put everything together, we're going to start out with this TAMP system that works but uses low quality distributions. We're going to solve the new problems we face, and we're going to store the data of the samples that lead to success in those tasks. We're going to measure how well we can solve the new task, and we're going to train the generic and specialized distributions and auxiliary models, and we're going to use those to construct our mixture distribution in the next loop. And then we're going to repeat this throughout the lifetime of the agent. So let's have a quick look at how the system works in practice. The folks at Stanford released this great benchmark called Behavior, where this funny-looking robot is in charge of solving a range of complex, long-horizon household chores. What we'll do is we'll have the robot run through these tasks one after the next, collecting data and improving its samplers over time. So very briefly, what we see is that as the agent progresses over time, the efficiency of it solving problems grows better and better as compared to the poor samplers that it started out with. So as the robot is deployed for longer in these virtual homes, its capabilities for drawing good samples improve over time. For example, we might start out by asking the robot to tidy up our home office. So it'll come up with this high-level plan to go to these folders here and bring them to the cabinet out in the back. And the red dots are samples from the distributions that it has been learning. And then the robot is going to move on to a next task where it has to pick up these cans that are scattered around the room. And it will leverage the distribution for grasping folders, which are somewhat similar, but it'll still have to specialize to the cans. And the robot will continue doing this over the sequence of tasks, one after the next. Stepping back a bit, we ended up with a system that leverages temporal and functional modularity to learn these highly complex and long horizon behaviors. In these videos, the robot is making several thousand low-level decisions, but the planner only has to make 10 or 20 abstract decisions and then refine them with a sampler that the robot has been learning over time. This idea of having a robot that learns over time but starts out with a working system is going to transform the way we deploy robots. But there is still a long way to go. The sampler learning problem that we talked about requires a fixed system that already works and a set of skills that have been pre-computed in some factory stage. But a lifelong learner should be able to learn new skills over time as they become necessary to handle new problems, skills that we may not have thought about during design. As robots are deployed more broadly, the amount of data that we have of real robots is going to grow drastically. And so we need to be able to leverage data from across many homes in a way that both maintains specialization to each user's preferences and that preserves the privacy of each user's data. And in today's day and age, we need to be able to leverage the power of large-scale pre-training data. But we need to come up with algorithms that allow us to do that in a way that the pre-trained models can adapt over time after they are deployed. And as I discussed in this recent blog post, modularity is going to be the key that enables these capabilities. Of course, all this work would not have been possible without the help of my fantastic collaborators. Thank you, and I would be happy to take any more questions.
All right, thank you, Dr. Mendez. I think this is a wonderful talk. At the beginning of the talk, as I was reading your bio, I was very curious how you put all these pieces together: reinforcement learning, planning, and transfer learning, and robotics. But yeah, your talk very clearly illustrates how it works, and like all these pieces feel very necessary. And yeah, it's an amazing talk. Thank you. Yeah, we can take some questions. I think it's almost 1, but we started late, so maybe we can take maybe 5 or 10 minutes of questions if you have any. Feel free to. Yes, I can. I'll turn on the voice lift system so anyone can feel free to speak up, and the Zoom will also capture the voice. And folks on Zoom, feel free to also just unmute and ask your questions.
Was there a way that the earlier talk like ties into the later half, or are they kind of like different on a different like level in the hierarchy?
So hopefully folks can hear me. I turned off my mic just so we don't have multiple mics going on. They tie together in terms of the motivation of using functional and temporal modularity, but not in terms of the approaches. The approaches are quite different. But the idea that we can break apart a system to learn each of the pieces separately, which is what makes it possible to do lifelong learning, is the same one that motivated both of those ideas.
Thanks again for the great talk. So I have a question about this lifelong like planning phase, like long-term planning. So if the robot fails a task, how your approach can handle like this kind of failures? For example, you show this like navigation and pick and place and some manipulation task. But how about when the robot fails the grasping, like the object just drop off from the gripper? Yeah. So let me.
So the idea of task and motion planning is that it's like the most common scenario is that you try a grasp and it doesn't work. And so the idea is to backtrack. And so here we're making the assumption that we have a simulator that tells us whether the grasp will succeed or not. And so what we can do is we try the grasp, and if it doesn't work, we try another grasp. And if it doesn't work, we try another grasp. And eventually at some point we decide, well, let's backtrack. Maybe the problem is that the robot is in the wrong position. So it should backtrack, come up with a new position to navigate, and then retry the grasping. So if you had to do this in the real world, if you don't have a perfect simulator that tells you whether things will work or not, then I guess you would have to do replanning, but that will be costly. So hopefully you have useful simulators. They don't have to be perfect, but you want to minimize how many times you have to replan on the fly.
I see. So I saw like your work is on this lifelong robot learning. Did you consider any like online or on the fly adaptation?
Can you clarify in what sense?
So generally, like the discrete work generally shows how the robot accumulates knowledge over time. But I mean, by online adaptation, whether the robot can sort of like adapt its behaviors without learning, but still show some adaptability.
Oh, interesting. No, we have not, but that sounds like it's very connected and definitely something that we should consider. But my work has not done that. I think it's this idea of having a robot that it's basically the idea, okay, you don't need lots of data. Sometimes on the fly, you have to figure out, how do I solve this new problem right now? So that sort of adaptability is very relevant to lifelong training, but we haven't done that in our work. Great, cool, great question. Yeah, let's take a question.
So it's about the earlier part of the talk. So when you have this like modular learning, does it require the tasks need to be like sufficiently distinct? For example, like what happens if your tasks, like some of the tasks are like exact copy of other tasks, but we don't know it? Like,
that's a great question. That will have some implications because, for example, if you're learning a module and it sees, oh, all these tasks require the exact same thing, then all the modules will somehow try to overfit to that. Now, if you have only a couple, then that shouldn't matter because you'll learn 2 separate modules. They'll both do the same thing, but because you have other modules that do other things, the previous modules in the chain and the later modules in the chain will still have to learn to work with all those different modules. But if you have many of these problems, like if you have 4 modules that are the same and one that is different, you're probably going to end up specializing all the rest of the chain of modules to these 4 things that are the same.
That's a good question. Yeah.
I'm asking because it's like it's in the artificial setup. It's like easy to kind of design tasks that are like distinct, right? But I think for lifelong learning, it's like for your ultimate goal, right? Some tasks, new tasks come that is like exactly the same than the task they did before, but it's like we don't know it just because they can.
Yeah, no, that's a good question. So and yeah, so I think I mentioned this at some point. We are assuming that somebody tells us what task we're taking, but in practice, the robot might have to do not exactly the same thing twice, but very similar things, right? Maybe it's in some different state or something like that. So we do need mechanisms. I mean, for example, in the TAM setting, you know exactly which modules you're using all the time. The TAM system decides which modules to use, so it's not like it's brought upon the system by the environment. The system determines which modules it has to use. And so in that sense, you would kind of sidestep that problem. But that's a good thing to think about.
There are a couple of questions in Zoom.
Yeah.
So there was an earlier question also from like the earlier part of the talk. Another question. So also, how does the robot determine if a task is different or the same? It's probably related to my question. When does it retrain the module or just reuse it?
Yeah, let's try to go to this. Here. So the idea is that every time the agent faces one new task, it's going to have 2 stages. In the first stage, it trains new modules, and in the second stage, it pushes all the knowledge that it just acquired back into the shared set of modules, and then scratches the new ones, right? So we're not really growing this, we grow over time if we need new modules. But if we copied over a module, we're not going to keep 2 copies of the modules. We're going to consolidate them in this accommodation stuff. We're going to consolidate everything together into one single repository of modules.
Yeah, and there was a question related to this. Is like if we save the data in the modules as new tasks come, won't the history increase in size indefinitely? And I think we can just
Yeah, for sure. I mean, so one addendum to that answer is that like data storage is not too expensive. You get to store lots and lots and lots of data. I think for people that have worked in the lifelong or continual setting, one of the challenges that really makes it hard to train when you're accumulating more and more data is that training becomes slower and slower. Right? You have a growing data set, then every time you have to go back and retrain, it gets slower. The fact that our system only does that kind of in a short stage, so most of the time it's just exploring on the new task, and then it's going to push back knowledge in a shorter, like post-training stage. I think that handles some of that difficulty.
Thank you.
In the first half of the talk, you sort of enforce modularity, where you say that these problems we should enforce modularity to help us have these modules. Have you thought at all about ways that this modularity could become emergent through the actual learning process, like with neural architecture search or with pruning or with evolution upwards? Something like that?
Yeah, absolutely. So we do have some work before this on the supervised case where we sort of do the process of determining the modularity autonomously. So the system searches for it's very similar to neural architecture search. So the system determines what is kind of the modular structure of the task and then then trains the modules that it discovered and so on. So yeah, for sure, I think that's a very important line of work. I think in robotics, we know a lot about the structure of the robot problems that we're facing. And so like just as a learning problem, I think it's very interesting. I think for robotics, we can get away with enforcing the modularity most of the time.
Curious about like what kind of state spaces were like the inputs here? Did you train these on like visual inputs or were they on a joint level inputs?
Yeah, we get the joint positions and the positions of the objects and so on. So it's like it's a 60-something dimensional vector that encodes a bunch of information about the positions and joints and velocities and so on. Yeah, good question. Yeah.
I was curious to know how we can apply some safety constraint in task learning or even skill learning, because an important concern in not just lifeline learning system, but any kind of adaptive system is that they will have less or sometimes zero supervision from humans. So it is really important to make the learning safe. It's not just about learning how to do a task, also it's about how to do that task safe.
Yeah, no, awesome question. So I think that there's sort of a two-part answer. In the reinforcement learning case, there's a bunch of literature on like safety and exploration and so on, and trying to enforce safety constraints, which is relevant. I think still reinforcement learning, like in the wild on its own, is not the safest thing in the world. So probably don't do that if you have an actual robot running around the house, or like an autonomous vehicle driving around the street. So don't do that. But I think one key idea here is that modularity makes it a lot easier to enforce safety, because now you can encapsulate your safety systems at each level, right? So you don't need the visual perception system to be safe. Like, that's fine. You need the decision-making and the control at the low level of the robot to be safe. And then you can impose safety constraints at very granular levels. And so in robotics, for example, you would impose like obstacle avoidance, and that would be a wrapper thing that goes on all the time and tries to avoid obstacles all the time. So I think the key thing is modularity allows you to bake in safety easier because you get to do it at the modular level. We haven't explicitly thought about that or tried it, but I think it's a promising direction to think about that. Great, thanks.
Great. There's no more question, then let's give Dr. Mendez another round of applause. We'll see you next week.